All right, so in the previous video, I think we learned how to calculate Z critical values. So I think we are almost ready to calculate a one sample T interval for P. In the AP course, they're kind of picky about naming your procedure. So this is a one samp Z int for P. This is what we're going to put down on basically all the problems that we do for this. Don't put a p hat there. You don't calculate confidence intervals for p hat. You know what p hat is. You have your sample proportion. You're creating an interval for this unknown p value. So be careful about that. So here's the formula. If you remember, confidence intervals are always your stat plus or minus your margin of error. That is your stat plus or minus your crit value times the standard deviation of the stat. So in this case, our statistic is p hat. Our critical value is a z crit because we're using a normal distribution to model this. And the standard deviation of the statistic is, now here's the, normally the standard deviation is PQ, well, no, not normally. The standard deviation is always PQ over N square root. However, we don't have P, so we use the standard error in its place. That's good enough. So name formula. In order for our 98% or whatever percent confidence interval to accurately capture the true proportion 98% of the time, the following conditions are necessary. And this is nothing new. This is straight from the unit on sampling distributions. Number one, random. Your data needs to come from a random sample or a randomized experiment. We'll talk about that a little later. 10% condition. When we're sampling without replacement, which is what we always do, your sample size needs to be less than 10% of the population. And large counts, NP greater than or equal to 10 and NQ greater than or equal to 10. Now, these are, we're going to use hats there because we don't have the P's, the true proportion, so we'll just put NP hat and NQ hat. So why are each of these conditions important? Well, the random condition is important so that X bar is an unbiased estimator. Basically, so the sampling distribution of X bar is centered about the true, I'm sorry, we're talking proportions now, the true population proportion. It's the thing that guarantees us that when we collect our p hats, they're going to be located in the right, they're going to be centered about the right spot. If we don't take a random sample, then it's going to be biased. It's going to be shifted to the left or to the right. So this is the most important condition. Second condition, this is for a condition, a check for independence. Technically, it's kind of like a pseudo independence, right? We don't have independence, but if the 10% condition is satisfied, we kind of have independence. It basically allows us to use this formula reliably. Like this formula is never quite, because we don't have independence, this formula is never quite right, but if the 10% condition passes, then this is going to be good enough. We'll just say good enough. What does that mean? It means that when we collect our sampling distribution, this formula is going to give us a good approximation for the actual standard deviation of that sampling distribution. The 10% condition fails, we're actually going to get our standard, the sampling distribution, the standard deviation of the sampling distribution will actually be less than this. So our interval is going to actually perform better than expected. So we don't really care too much if this one fails, but we still want it to pass. And then the last one is normal, it assures, okay, let me just write this. The large count condition assures us that the sampling, that this curve is approximately normal. That the sampling distribution of p hat. Oh, I can't believe I did an x bar up there. My bad. We're talking about proportions here now. Next section, we're going to be talking about means. The sampling distribution of p hat is approximately normal. We're actually working on means now when I made this video, so I'm getting a little bit mixed up. My bad. That's something you guys got to be careful about too. You got to, we're switching between means and proportions. Always be conscious of which one we're working with. So this basically assures us of the center. This assures us of the spread, and this assures us of this shape. So these three checks together kind of let us know that the sampling distribution is what we expect. All right. This one is kind of the second most important. So in class, we talked about this at a little bit greater length. Basically, if we have a 98% confidence interval, right? If this one fails, our 98% confidence interval, maybe it will only capture 96% of the time, or 95, or maybe even 94. Because if our sampling distribution is skewed to the right, when we use our z-score cutoffs, we might not get that 98%. We might get a little bit less. But if we fail it, we're not usually too terribly bad if we fail that one. It's just not going to work quite as expected. If we fail this one, we're actually going to capture 99% of the time. If our confidence interval is 98, and we fail the 10% condition, that means we're sampling a larger proportion than 10% of our population. There's going to be less variability than we predict. So we're going to capture more, 99% or 99.5. You might say, well, that's a good thing. But yeah, but the thing is, we want our 98% confidence intervals to capture 98% of the time. If we want a 98% confidence interval and we fail this check, then we should modify our standard deviation, and we can narrow our confidence interval and get what looks, then a smaller range that is going to capture the right percentage of time. So although it fails conservatively, it still isn't the right interval. This is the kind of the big one. If you're creating a 98% confidence interval and you don't randomly sample, you just survey your friends, or you just survey Republicans, or you just survey guys or girls, or whatever your question of interest is, your 98% confidence interval might only capture 30% of the time. If this one fails, you're really, it could be really, really inaccurate. All right. So they're all important, but to varying degrees. All right, so the College Board and me, because I'm teaching AP Stat, require that you show several steps when constructing and interpreting a confidence interval. You might think you just got to calculate it. Well, that's easy, but they want you to do a whole bunch of other things. To help you remember and organize your steps, you can use the mnemonic PANIC. Now, our book doesn't use it, but I kind of like it, and I don't know, whatever. You don't have to use it, but you have to get all the pieces, so. Stands for P, define the parameter of interest using the correct symbol, words, and context. A, assumptions and conditions. Technically, it's the conditions, but whatever, A, right? Check all three conditions. N, name the test. Now, when we start preparing for the AP test, you're going to see that you only have to name the test. However, for early on this semester, I'm going to ask you to name it and give the formula. Okay? So this is going to be a 2-point problem. Basically, I want this and I want that. Okay? And then I is actually calculate the interval. Go ahead and plug those values into the formula and give me the actual interval. And then last, and probably most important, is interpret. We are like we did in section 7.1. All right, so let's just do one example here and see how it goes. Mrs. Quinn's class took a simple random sample of 102 pennies and discovered that 57% of the pennies were more than 10 years old. Calculate and interpret a 99% confidence interval for the true proportion of pennies from the collection that are more than 10% old. By the way, the true proportion of pennies from the collection that are more than 10, that's the P step, the parameter of interest. The true proportion is called P, and it is the true population proportion of pennies from the collection, whatever, that are more than 10 years old. A, panic. Assumptions and conditions. Number 1, random. And go ahead and check it off. Why? Because they took an SRS. So then a brief statement. They took an SRS. So I kind of want you to, give me the check, and then just write a brief, as brief as you can, statement that talks about that illustrates what the check is exactly. So for this one, I'm going to say n equals 102 is less than 10% of all, too many L's on all pennies in the collection. Now, I don't really know if this is true or not. I'm assuming, I guess, that there's more than 1,000 pennies in the collection. If that bothers you, you could put the word probably here, is probably. But that's kind of the check. If we got more than 1,020 pennies, then we're good. If we got less, then we're not. But I'm going to check it off. Large accounts. Check. We probably should check it before we, whatever, NP, now I don't have P, so I'm going to put in NP hat. That is, by the way, what is our P here? I don't mean, P hat is 57 out of 102, which is, oh geez, got a bunch of stuff here. 57 divided by 102. 5588.5588. So we need to take 102 times my p hat, which is 57 over 102. You can easily see that that's 57. It's sometimes it's called the success failure condition. Now you don't really need to write this down. You can just say it's greater than or equal to 10. Check it off. And q hat, that would be 102 times 1 minus 57 over 102. So it's greater than or equal to 10. By the way, that's going to be 102 minus 57, which is what, 45 or something? I don't know. Then a little statement here. So the sampling distribution of p hat is approximately normal. So what do you need? You need this. Actually, I take that back. You need this. Okay? If you don't want to put the n hat, p, q hat, n, q hat, you don't really need to, but you do need to plug in the right numbers. Illustrate that you know what numbers to plug into there, and then you also need to say something about normality. All right, so our conditions check. Oh, I'm running out of time. We got a minute and a half. We got to go fast. Name the test. One samp, z int, or p. And the formula, p hat plus or minus z crit square root p hat q hat over n. All right, because I'm running out of time, I'm gonna pause it and kind of do the next step because I need to keep this under 15 minutes. So I basically put in my sample proportion. I have a 99% confidence interval, so that's my z crit for that. And then I just put in my p hat, q hat over n. All right, now for 1 point, this is going to be 1 point for naming the test, 1 point for the formula. You could either do this or this. Type that in your calculator, hit enter. I put the plus in, I got the upper bound. And I put the minus in, you get the lower bound. So my interval is from 0.432 to 0.686. Okay, so that's actually the I step, the actual calculation of the interval. Feel free to pause it. I'm sorry about this. So my interval is from there to there, and then the conclusion is simply, we are 99% confident that the interval from 42.3 to 68.6 captures the, and then you're just going to put down your proportion statement right there, right there. That's how we kind of construct our